Hi everyone, so today's topic is probability. So in the last lecture, we learned about sampling, and also in the class, we spent some time on designing experiments. So to know the probability, we need to know first what is random phenomena. That refers to a situation where we know what kinds of outcomes can possibly occur, but we don't know which particular outcome will occur. And so there are some concepts that we need to know to define the probability. One is trial, that is each occasion when we observe a random phenomenon. And the outcome event, that is the value of the random phenomenon. And sample space includes all possible outcomes. For example, let's say I draw some color balls from a bag, and then there are red, green, and yellow balls. And then the possible outcomes could be red, green, or yellow. And if I toss a coin, I can get head or tail. And if I toss two coins, I can get two heads, heads tail, and tail head, and tail tail. The set of these possible outcomes we call sample space. So to define the probability, we need to know the law of large numbers, LLN. When we repeat a random process over and over, the proportion of times that an event occurs settles down to one number. That is probability. But there are two key assumptions in law of large numbers. One is no changes in the random phenomena over the repeats. So as we repeat the random process, there should not be any changes over time. And also, we assume the independence among the outcomes. So each event have to happen independently. So the probability doesn't tell us anything about short-run behavior, because probability really means about the results of large number of repeats. And also, the long run is really long. So multiple repetition, for example, 10,000 times. So don't expect the probability tells you a short-term trend of something. So there's an example. So this is from another textbook. This is showing the probability, estimated probability of getting heads when you are tossing a coin. And in this simulation, a coin was flipped 30,000 times. And as you can see, with a small number of repetitions, the estimated probability of heads are highly variable. It should be reached to 0.5, but it only happens with a long run, a large number of repetitions. So many people forget this and overinterpret results from small samples. So Tversky and Kahneman termed this as law of small numbers. We talked about this in the first class. In the fields of science, many researchers agree that there is a replication crisis recently, and this is one of the major sources, that small sample size. So if you run a study with a small sample size, the study findings is unlikely to be replicated. So you have to have a large number of samples to do the replicable research. So let's talk about basic rules of formal probability. The first rule is for any event A, the probability should be smaller than 1 and larger than 0. It's simple. And the set of all possible outcomes should have probability 1. That's a basic rule. And the probability of an event not occurring is 1 minus the probability that it occurs. And the fourth rule is an addition rule. And probability of A or B equals probability A plus probability B, given that A and B are disjoint. So they are mutually exclusive. They don't occur together. And there is a multiplication rule, that is probability of A and B is probability A multiplied by probability of B, given that A and B are independent. So in the general addition rules also include the case where the events are not disjoint. So let's start with the example, that is survey of college students, and 56% live on campus and 62% have a campus meal plan and 42% do both. And then what is the probability of living on campus or having a campus meal plan? Probability of living on campus or probability of having a campus meal plan. That is, we have to subtract the probability of living and having meal plan. 0.56 plus 0.62 minus 0.42, that is 0.76. We can express this with a diagram, right? So 56% live on campus, and 62% has a meal plan, and 42% do both. We are asking the sum of this area, so we need to add these two and then subtract this area from this. And what is the probability of living off campus and not having a campus meal plan? So that is not living on campus and not having meal plan. That is 1 minus probability of living on campus or having meal plan. So that is just 1 minus 0.76 and 0.24. So as you can see here in these calculations, general addition rules can be expressed like this: P, A or B equal probability of A plus probability of B minus probability of A and B. To talk more about the independence, we need to know what is conditional probability. Again, let's use an example. Let's say we surveyed 478 elementary school students and asked whether their primary goal was to get good grades, or to be popular, or to be good at sports. And this we call contingency table. So in one side there is a goals, and the other side there is a sex. And boy and girl has different goals, different numbers for each category of goals. So we can ask probability of having goals to be good at sports. So 90 over total number. So 90 divided by 478 equals 0.188. Probability of being girl is, of course, the 251 divided by total number. That is 0.525. And we can also calculate probability of sports and girl. That is this cell. So 30 divided by 478 equals 0.063. You can ask the probability of sports given girl. Given that you are a girl, what is the probability of having the goal to be good at sports? So that is a conditional probability. We can calculate that 30 divided by the number of girls. So 30 divided by 251, that is 0.120. And that is actually probability of sports and girl divided by probability of girl. Because this canceled out each other, the calculation is same. With this, we can talk about general multiplication rule. To remind you, the fifth rule was the probability of A and B equals probability A times probability of B when they are independent. But we can get its general form. So P, probability of A and B equals probability of A times probability of B given A, or probability of B times probability of A given B. How is that the case? So it makes sense because probability girl and sports is probability of girl times probability of sports given girl. From the previous slide, we were able to calculate the probability of sports given girl with probability of sports and girl with and the probability of girl. So if we move this term to the left hand, it becomes probability of sports and girl equals probability of sports given girl times probability of girl. So it's the same. I'm talking about the same thing. So here, probability of girl is 251 divided by 487, and probability of sports given girl is 30 divided by 251. These are cancelled out so that the calculation makes sense. So what's independence? We talked about the multiplication rule where PA and B equals PA times PB when they are independent. In the general rule, this P, A, and B was PA equals P times PB given A, right? So here, if we remove this assumption, so these should be same. So the independence means probability of B given A equals probability of B. That is the definition. And thus, if A and B are independent, this becomes true. But what is the meaning of independence? So independence means the occurrence of A does not change the probability of B. So the condition of A does not change the probability of B. That is the meaning of this equation. And that's a little bit different from disjoint. Disjoint means they does not occur simultaneously. They are mutually exclusive. I mean, in the real life, we use this independence for this meaning a lot. But in statistics, independence is different from disjoint. Now we are ready to talk about Bayes' rule. It's really important and really interesting. And that's basically reversing the conditioning. Let's say we have this value, probability of A given B. And can we calculate probability of B given A from it? To calculate it, we need to know the probability of A and probability of B, because we just learned this, right? And probability B given A equals this from this equation. Is the same thing. Remember this. We can express the equation like the following, right? Probability A and B, we change that with this. This basically tells us how to convert probability of A given B to probability of B given A with the probability of B and probability of A. And probability of A can be expressed as probability of A given B times probability of B plus probability of A given not B times probability of not B, because this is the probability of A when the B occurs, and this is probability of A when B does not occur. Then we can express this equation with this. So we usually call this as Bayes' rule. We use these two equations altogether. Let's talk more about this Bayes' rule. Let's say you have a test that is a really good test, because when a person has a disease, the probability of getting positive results from the test is 0.8. It's 80%. Highly sensitive. But when you change this, reversing the conditions, it turns out the probability of having disease given positive results from the test is really low, like 10%. How this can happen? Okay, let's calculate a little equations from this. A as a test plus and B as disease. And we can just use this equation using these notations, and then we can move this term to this and become this, and then right side we have probability of test positive divided by probability of disease. From these values, this is 8, right? When it's possible, if the diseases are really rare, for example 0.0001, prevalence among the population is 0.01%, and then if the test positive results occurs, for example 0.08%, only 0.08%, and then the ratio becomes 8, and then this can happen. So in many cases, the disease prevalence is really low. So there is a really good video on Bayes' rule, and I again recommend this guy's video, Veritasium. In this video, he provides another idea where we can think about this Bayes' rule as an update of our belief. So the first test results came out to be positive. Let's say A here is again test positive and B is disease. The prior belief about the disease, the best prior is the prevalence. If the prevalence is really low, like 0.0001, and then even if we have really high value for this is when I have disease, the probability of getting positive results. Even with a high value for this, we are gonna get really low posterior probability. We call this as posterior. But let's say we got the second test results from another hospital. Just I want to know my diagnosis is right. And then again, I got the test positive, for example. And my prior should be this. So best P probability of B having the disease is not the prevalence, is not the population level proportion. That's based on the first test results. And then I updated it if I have the second results, again, positive, and then this becomes really high. So it's basically the updating process. Probability of B given A becomes much higher than the first time. So I really recommend watching this video. So you can picture the probability using tables or Venn diagrams or trees. You might be familiar with this, but there are other ways. Okay, that's it for today's class. And don't forget, complete the quiz that's in the note. Bye. See you in the class.